Hello everyone, welcome to IoT Slam 2017. I'm Naveen Balani. I lead the IoT and cognitive research for Accenture Labs. In this session, I'll talk about how to build intelligent connected products using artificial intelligence, machine learning, cognitive IoT, and blockchain, along with various use cases related to these technologies. So, in order to build out intelligent connected products, you need a core set of capabilities, platforms, services, and architecture patterns. I refer to this as an enterprise IoT stack. The IoT stack comprises of many layers, starting with devices which communicates and send data to the core platform layer, either directly or indirectly through different protocols like MQTT, CoAP, over various communication strategies like Wi-Fi, Bluetooth, cellular, or low-powered wide area network. And these devices can also act as an edge gateway, which provides local analytics and protocol conversion support. For instance, converting low-powered radios like Zigbee to Wi-Fi in a home automation scenario. And I'll talk about Edge Gateway in detail in the next few slides. The core platform is typically implemented as a message-oriented middleware, which provides a set of key services to allow devices to connect securely, store and replicate the data for fault tolerance, and provide scalable technologies to accommodate millions of connected devices whenever required. And there are commercial IoT platforms available. You could use providers like IBM, Amazon, Microsoft, or build one using open source frameworks like Apache Kafka. Once the data is made available to the platform, the analytics platform lets you analyze large volumes of data in real time as well as in batches to discover actionable insights. And as part of discovering insights, you basically learn from machine data. You develop, train, and test out machine learning models for various use cases like anomaly detection, causality analysis, predictive maintenance, and invoke the model at runtime and take possible action. The key here is based on the data, you design and develop algorithms. And data in a IoT context can be broadly classified into four types. It can be structured data, a sequence of data or time series information from sensors. It can be unstructured data, like images being captured from drones. A combination of structured and unstructured data, like in case of augmented reality, where you superimpose images and text to derive an outcome. And fourth being behavioral data, where devices learn from interaction. Basically, the entire cognitive aspects of the device kicks in. Each of these use cases requires separate architecture and algorithms, and based on the use cases, the computation needs to happen on the edge, cloud, or a hybrid approach. For instance, if your use case was around security and surveillance, you would probably employ computer vision technologies at the edge for processing and analyzing the image locally, as it doesn't make sense to stream the data over the cloud. And I'll talk about one such use case as part of this presentation. The next is the cognitive layer, which allow connected products to learn from behavior and insights and provides a natural extensions to one's digital life. And in a connected world, you would have a stronger connect between man and machines, where devices would be able to learn from you. You would interact with devices using natural language, use technologies like facial recognition, and so on. And I'll talk about how do you go about building cognitive IoT apps as part of this presentation. On top of the stack, we have the solutions layer, which provides end-to-end consumer or industrial IoT applications, which are developed using the various stack services. Apart from this, the IoT stack should also address various cross-cutting concerns like security and management of IoT applications. And this requirement includes device management, device security, secure bidirectional communication between devices and the IoT platform, application security, network topologies, deployment and simulation. And I'll talk about one such use case on using blockchain for trust and compliance. Next, I would talk about how do you apply intelligence to each of these layers in the enterprise IoT stack. I'll talk about three architecture patterns and solutions on how do you go about applying intelligence at the edge, in the cloud platform, and a hybrid approach. The first use case is on using computer vision technologies at the edge for various security and surveillance activities. For instance, you would like to detect suspicious activity at an ATM. Simple cases like people wearing helmets and entering the ATM, to unusual movements, or you would like to capture identify object in remote areas like using drones to identify croplands in an agriculture plant, or for various defense related activities. In this scenario, you would need real-time decision making at the edge, as it might not make sense to transfer the data over the cloud for processing, be it for latency issues, bandwidth, or there might be no or very limited connectivity. In this case, you would employ intelligent devices at the edge. In order to build out this solution, you will need to employ computer vision algorithms on the edge. You can build this using commercial available APIs or using various open source deep learning frameworks like Tiana, TensorFlow, and Caffe, which are used for solving computation problems using deep learning. For those who are not aware of deep learning is a branch of machine learning for learning multiple levels of representations through neural network. And the neural network and image processing would automatically infer rules for recognizing images instead of you extracting thousands of features to detect images. And various deep learning architectures are employed like convolution neural network, recurrent neural network to solve specific problems like computer vision, natural language processing, speech recognition, and have achieved state-of-the-art results. For computer vision, we use a convolution neural network. We could build a convolution neural network or use one of the pre-trained instance. For instance, we could use an inception model released by Google, which is a 22-layer deep network which achieves state-of-the-art results for classification and detection of images. And to provide some context on how this works, for a computer, image is nothing but a vector or a set of number pixels. And convolution neural network preserves the spatial relationship between pixels by learning internal feature representation using small squares of input data. And features are learned and used across the whole image, allowing for objects in the image to be shifted or translated in the scene and still detectable by the network. For instance, in case of a helmet, some network would learn it has a round edge, some may learn it has to have a glass pane in the front, and so on. So the idea is, irrespective of where the object is in the frame, you should be able to identify the image. The following slide shows the stack view of employing deep learning API on the edge. The stack consists of real-time OS, a deep learning library, the learning model, and the classification code for classifying objects. The learning model is essentially some representation like an object graph which is derived from training the images. So how do you go about implementing this? I'll talk about one approach for building this out. You could start off with building your own convolution neural network or start with a pre-trained network like an inception model. Next, you would go about training the network or just retrain the last network in case of a pre-trained network. For instance, you could take the existing inception model and network released from Google and retrain only the final layer from scratch using your set of images. This process is known as transfer learning, and it cuts down the training cycles from days to few hours based on your training data. Next, you would go about optimizing your network by trying various learning rates, image crops, batch sizes to get the desired level of accuracy. And coming up with the right set of hyperparameters is one of the toughest part in deep learning. And once you get the desired level of accuracy, yeah, you can use this model for classification. For TensorFlow, the generated model is an object graph. Next, you would go about deploying the TensorFlow API and the train model on the edge gateway and use the classification code for classifying objects. The other point to keep in mind is that these deep learning libraries are bulky in nature and might not be supported on all hardwares. A lot of optimization need to happen in hardware for providing the desired performance, and there are a lot of innovations happening in this space to provide optimized libraries for deep learning at the edge. To provide some insights based on our experiences building a computer vision application, we built out a portal called internetofbirds.com, which recognizes birds from the Indian subcontinent and have achieved state-of-the-art result. The idea is to take this technology on edge devices and drones for tracking various environmental production activities like identifying, tracking various animals and help in conservation activity. Same technology can also be made available on phones in an offline mode. So classification and detection of images can happen locally, and one can use other contextual information like GPS coordinates to identify the location along with the entity. And to get started quickly, once I had the model, I ported the model and the libraries to a Raspberry Pi device, attached a camera, installed it outside a test area, and was able to detect and identify most of the bird images. So this is a portal we developed. You can try it out. It's publicly available at internetofbirds.com. It has a simple interface where you can go and upload a bird image and the system would identify the type of the bird. In this case, the bird was identified as Indian peafowl, and different messages are displayed based on various levels of accuracy. Next, I would like to talk about my second use case on building intelligence on the cloud using cognitive technologies. Cognitive IoT is about enabling current IoT technologies with human like intelligence. The end goal is to provide expert advice based on the domains being targeted. Cognitive IoT has three key features. Basically, the system understands the domain like a human does, and based on the understanding, you can reason and answer various information about the domain. And third being a continuous learning process to improve the knowledge and answer various other information based on interactions and feedback. Cognitive IoT technologies can be applied on the edge or in the cloud as part of your solution. The first example I like to provide is how to apply cognitive IoT technologies at the cloud for a sports domain. In a sports domain, there are actually three primary use cases: learning from an expert or a coach and improving one's game; personalization, where all the information is personalized to sports person to improve his game; and continuous learning to keep improving based on the current and past records. So I'll talk about an example of a cricket game. For those who are not aware of cricket, cricket can be viewed as similar to baseball. Both are bat and ball games, but cricket has a lot of variations. The real value that we want to derive is to enable batsmen understand the game better, help them master various batting strokes like cover drive, pull shot, help them analyze their performance continuously to be an expert batsman. For instance, what should it take for a batsman to bat like an icon like Sachin Tendulkar? With respect to the bowler would like to understand how well he is bowling, his speed, his run up, the way he delivers the ball. All these insights can help him improve his game continuously and how similar he is bowling to an expert bowler. So, how do you go about realizing this use case? You start with putting embedded devices inside the cricket ball without much increasing the form factor. And there are a lot of regulations on the form factor of cricket balls. So you're looking at minute embedded devices which provides at least 6 axis sensor for accelerometer and gyroscope to identify any movement in three-dimension space. Second is embedded devices on cricket bat, pads, gloves to identify batting strokes and movement. And finally, a connected stadium to capture images of batting strokes and bowling movement. For instance, the right posture plays a significant role in delivering a great batting stroke. So, combining image and motion data from devices and developing an algorithm to look at both these contexts and provide a recommendation and insight to improve a player's game. From an architecture stack perspective, you have a low powered device which is installed inside the ball or embedded as part of the design and manufacturing process. A motion SDK is installed on the top of the device to identify any movement in general and communicate the reading back to the cloud. In the cloud, we have the learning model or the training data. Basically, we would ask an expert batsman to bat and play various expert strokes like cover drive and record their movements. This would be used as a training test data and comparison would be made against it. Here we would be comparing 3D models, so machine learning approaches like dimension reduction can be employed. Many new innovation approaches can be applied to compare and predict to motion in three-dimensional space. Similarly, training data is captured for an expert bowler along with other contextual information like hand movements, pitch angle, and so on. This feedback is continuously captured and system provides guidance for improving a person's game. The player can also track all the information on his mobile also. The same technique and concept can be applied to any sports game to get cognitive insights. At the end, what we're trying to do is to give personalized and continuously expert advice to a sports person to improve his game continuously. The third use case I like to talk about is how to apply intelligence at the edge and the cloud using a connected car example. When it comes to cognitive intelligence, in my view, there are three primary use cases. The first being expert guidance. The real value is derived through expert guidance. Think of this as an expert looking at the car and providing details on your maintenance activity based on actuals or providing predictive maintenance alert. As you start driving the car should learn from your behavior and provide recommendations on your driving patterns and also provide suggestions to improve your car mileage. The second use case is personalization. Personalization is about providing recommendations based on your data interaction with the car. For instance, the car should be able to recognize you through facial recognition. Car should be able to play your favorite music station. You should be able to speak or chat with your car through a natural language interface. You might have bought a new car and want to understand all the features of the car. You can ask questions like how many dual airbags are installed, when is the next maintenance cycle, and the car can even point out features of the car that you haven't explored so far. The third use case is the ecosystem use case. I refer to this as connected the connected. And connected the connected use case is all about using the car data for new innovative solution. And the real value in a connected world would be derived from how the connected data would be used in context of other applications which provide new innovative business solutions. For instance, for a connected car solution, the connected car data can be used for paper usage, insurance, after sales services, autonomous driving, and so on. Next, I'll talk about general guidelines on how to build a connected IoT car solution to realize various use cases like condition based maintenance or driver behavior analysis. So, this slide is a high level interaction overview of various architecture components that I talked about in my first slide. From the connected car, you can get the vehicle data, which is comprised of onboard diagnostic information, acceleration, brake movements, GPS data, and this data is continuously streamed to the IoT platform. You can also have a edge solution installed on the car which streams only the required data back to the cloud. For instance, some algorithms can be applied locally on the connected car. For instance, facial recognition, where the car would open up based on recognizing your face. Another example could be of the connected car data being streamed back to the cloud for driver behavior analysis. Once the data is made available on the platform, it is typically stored for historical purpose. The data is then filtered and streams of data are acted upon, coupled with asset data, which is a static data about the car like optimum temperature, pressure of car tires, which are required for condition based monitoring and alerting the driver. And if you see, the real value about the solution is not the platform and the technology, because you could build this using open source technologies like Apache Kafka, which you can use as a messaging platform, Apache Spark as a streaming infrastructure. But the real value is how are you analyzing the data quickly and what insights are you deriving from it. And that's where you build and deploy machine learning models to learn from this data. Following is a general approach of developing a machine learning model. The machine learning model take three inputs: historical data, asset data, and the runtime data. The historical data would be the maintenance record of the car. The asset data for a connected car would be static data about the car. Like each car would have different specifications, number of engine containers, etc. For the driver behavior analysis use case, this would hold permissible speed limits based on GPS coordinate. And the third is the runtime data, the actual data of the connected car. And together, all of these are used for predicting an outcome. The first step in any machine learning process is to cleanse and normalize the data, then train and evaluate iteratively to get the desired level of accuracy, and deploy the model as a service which can be called as part of your application. You can try out various machine learning models like regression and classification, or create an ensemble model to provide improved results from various machine learning models. And this completes one end-to-end flow. The third technology I would like to talk about is blockchain. In a connected world, the real challenge would be around trust, compliance, and security, and that's where blockchain can aid in solving the missing puzzle for a distributed IoT implementation around trust and compliance. Blockchain can be viewed as a distributed, decentralized database that holds transaction of every entity that is transacted through the network. Blockchain technology manifested from Bitcoin, a type of digital currency created and held globally without any central authority or middleman. And Bitcoin uses cryptography to control its creation and transaction, and a public ledger called the Bitcoin that I described earlier. In a connected world, you would see a wide variety of devices that needs to be connected or transacted to get some work done in an autonomous way. For instance, take an example of a connected car solution. How do you ensure the part being replaced in a connected car are new and genuine? Can this be from different manufacturers? What is the life cycle of the new device? Can this new device connect to existing devices? What all services was done in the old device? The other example is of a connected home, where you bring in a new device. Would that be allowed to connect to other connected devices? Many of these can be first time interactions. For instance, a home automation device like a security alarm would need to integrate with various devices from different manufacturers, which needs to set the right context to raise an alarm to the security device. The fundamental question arises, should the devices be allowed to connect and communicate with each other? And what is life cycle of the device? And there are a lot of challenges around authenticity in the simple use case, and everything in the end boils down to trust between the devices and who maintains the trust. And to solve a part of this problem around trust and authenticity, you need an entity, basically a set of entities which can track the entire life cycle of devices, and probably a set of contracts which can help devices to connect with each other in a secured way. One can start with embedding devices with blockchain API right from the manufacturing process to track the entire life cycle. Smart contracts can be built, like devices from pool of manufacturers can work seamlessly. The other example could be of trade and finance for food and groceries, where smart contracts can be applied, which receives parameters like temperature from shipping containers to ensure optimum temperature is maintained from food getting spoiled, and the payment released automatically when the shipment is delivered. And in my view, apart from the technology, the real challenge is the mutual acceptance from the entire IoT ecosystem, its usages, and government initiatives on setting up a regional blockchain registry. Once deployed, it can aid in other use cases also, like security and compliance for ensuring devices that are not allowed to cross geographical boundaries. In this slide, I'm providing a reference on how to go about building enterprise IoT applications using enterprise IoT cloud offering or open source software. From a strategy perspective, most of the commercial IoT cloud providers have the same strategy of providing the IoT platform and a set of services to enable development of scalable IoT applications. You can also use the IoT platform with various other complementary services offered by the cloud providers like caching, mobile push notification for sending alerts, or blockchain. The following provides a summary chart of various services offered by the cloud providers and open source alternatives which can be used to build IoT application. The chart is also available on my blog, and I've provided the link below in my slide. As you see, you can actually build out IoT solutions using open source technologies like Apache Kafka as a messaging platform, Apache Spark as a streaming infrastructure, Spark ML for machine learning, Ethereum from blockchain, and a custom protocol bridge for converting IoT protocols like MQTT to Kafka messages. In my view, the real value is not the platform and services, but how can you harness the data coming from connected objects and other contextual information to discover pattern and correlations in real time to positively impact businesses. The biggest challenge would be to make sense of this data, identifying data that can be consumed and quickly act upon to derive actionable insights. Edge analytics would play a crucial role, and more algorithms would be developed specifically for edge processing. I also feel the use of artificial intelligence technologies like deep learning will be a key differentiator to derive insights rapidly from massive streams of data. To sum it up, I like to conclude by saying IoT is the senses, data is the fuel, and artificial intelligence is the brain to realize the future of a smart connected world. With this, I would like to conclude my presentation, and if you need more information around any of these subjects, please feel free to email or refer to my book called Enterprise IoT, where I've explained each of these concepts in detail. Thank you all for listening.